Hello everyone, welcome back to another video of Maths 215. In this video, we shall be discussing about the notion of holomorphic or analytic functions. Now, what are holomorphic or analytic functions? These are the functions that take one or more complex valued inputs in the functions, where you have function f of z, which would give you some output, w, and it's something you know already. Now, a function is said to be function f is said to be analytic at z0 if it has a derivative for each point in some neighborhood around z0. Now, this statement states f of z0, as in f of z0 is said to be analytic if there exists a derivative for each point in some sort of neighborhood around your point z0. Now, furthermore, we say a function is analytic or holomorphic. These two terms, analytic and holomorphic, these are sort of interchangeable with each other. So, which is why I gave holomorphic / analytic functions. In complex analysis, they both mean the same thing. Yeah. So, a function f is analytic for a given domain D, as in the function f takes points z, which are elements of the domain D. Function f is analytic for a given domain D if its derivative exists for all points that are in the domain D. Pick any point in the domain D for which the function is defined, and if that point, if any of the points are differentiable at that domain D for the function f, then we say that the function f is analytic. Now we have more theorems. Now I would like to say the following fact for this course is that don't get lost in the definition. These are just statements, but do not get lost in them. These are just simple definitions. There's no point in memorizing them either. Just try and understand them. A very important fact about holomorphic or analytic functions for complex variables is the fact that holomorphic functions, if the function is holomorphic, are infinitely differentiable. As in, you can take the derivative of the function f infinite times and the derivative will still exist. And then it's still differentiable. Also, a very important part, which we're going to see in the future videos regarding Taylor and Laurent series, is the fact that f of z, if it is holomorphic or analytic, can be expressed in power series format. Don't worry about this too much because we'll get back to this when we're going to discuss Taylor and Laurent series. Now, I would like to show an example of a function which has some analytic behavior but also has some weird behavior. Take for example a function f of z, which is equals to 1 over z. Now, this function is analytic for all points of z except for z is equals to 0. As in, for the function to be analytic, fully analytic, we must have the following condition, that z cannot be equals to 0. But the analyticity of this function basically breaks down when you take, if say for example this condition isn't imposed, then the statement breaks down, as in f of z ceases to be analytic and z is equals to 0. Because, as you know, if you take f of 0 for this function, where f of z is equals to 1 over z, you get 1 over 0, which is undefined. Now, this z is equals to 0 point is what we call a singular point, or a singularity of f. A singularity of f, which is basically what causes a breakdown of analyticity. We shall see further implications of singularities in further videos and future chapters. Now, it goes to show that the analyticity of a function depends on a lot of different things. One of them being continuity. As in, we saw here, f of z is equals to 1 over z. This ceases to be analytic at z is equals to 0 because it breaks continuity. It's relatively hard to show why it breaks continuity, because the mapping of complex valued functions is a little bit complicated. But if I show it for the real number case, say for example you have f of x is equals to 1 over x. Now we know, so this is, remember, I'm showing it for a real valued function. Basically breaks continuity here as well. If I simply draw it, this is for the real number case. I just want to show how it breaks continuity, and this is the mapping of a real numbered function. So this here is the graph of 1 over x. As you can see, we're breaking continuity here at x is equals to this origin, where x is equals to 0. In similar fashion, continuity is broken for the function f of z is equals to 1 over z. But the sheer fact of simple continuity, the breakage of continuity, or the fact that there might be continuity of functions does not simply prove that a function is holomorphic. You need more stricter rules. Now, the stricter rules are as following. I have given a few of the spoilers for these strict rules in the videos regarding Cauchy-Riemann equations for Cartesian and polar coordinates, but I would like to put them in a more strictly definitive manner. So, the sufficient conditions for differentiability must be maintained for it to be holomorphic or analytic. Since, as I talked so before, the function has to be differentiable for it to be holomorphic or analytic. So what are the sufficient conditions for differentiability? The first condition is that the first order, let's not denote it as with arrows, I'll use number 1 and 2 Arabic numerals. The first order partial derivative of functions u and v with respect to w dot r dot t means with respect to either x comma y in the, if you're taking your complex number to be in the Cartesian coordinate system, or r comma theta if you take your complex number in the polar system, must exist everywhere in the neighborhood. This is condition number 1. And we need another further condition, which is condition number 2. Condition number 2 is the fact that the partial derivatives, which you calculated here, the first order partial derivatives. So the partial derivatives also have to be continuous at x naught, y naught, or r naught, theta naught, and they must satisfy the Cauchy-Riemann equations. Now, with these two conditions in order, and the fact that your function f is continuous over a domain D, you will have that your function would be holomorphic or analytic. Now, I would further like to add is that fact that Cauchy-Riemann equations only hold true if your function is differentiable in the first place. So, just say for example you have a function, you don't know whether the function is differentiable at a point z0. Simply proving the fact that they do follow Cauchy-Riemann's equations does not necessarily prove the fact that it is differentiable. As in, if f is differentiable, I write it as diff at z0, then it proves CR relations or equations. But say for example you don't know that whether or not then it might or might not prove the Cauchy-Riemann relations. But if say for example your function, you don't know whether it's differentiable at z0, but if you find out in some happenstance or whatever the conditions may be, that your function does indeed prove that it maintains the Cauchy-Riemann relations, but that does not directly mean that it is exactly differentiable at z naught. Now, there are further more theorems about the fact. There are further more theorems regarding holomorphic analytic functions. The fact that if, say for example, you have two functions, f and g, both are analytic over domain D, both analytic in a domain D, then f, the function f plus g, whatever it might give, is also analytic over domain D. Not only that, but the function f times g is also analytic in domain D. Now both of them, both f and g, have to be independently analytic over domain D for these two to hold true. Furthermore, if you have these separate things, if you had f of z over g of z, where f of z and g of z are both analytic in domain D separately, f of z over g of z is also analytic, given that there does not exist a value g, as in there will not exist a value g in the domain D which would give g of z is equals to 0, as in this is valid, this is analytic in domain D if g of z is not equal to 0 for a certain value of z in domain D. Now I hope you understood this video lecture. I hope you will see in further example videos the use cases of analytic functions and how to prove whether a function is analytic or holomorphic. I would like to end with the following statement. The fact that these two keywords, holomorphic and analytic, these two basically mean the same thing for the case of complex analysis. Thank you and hope to see you again in the next video.